Start.
So there is a delay, right, from here to YouTube?
Yes, sir.
I don't see anything. Okay. Okay. So welcome to the live session of high performance computing for scientists and engineers. We earlier had a similar live session once our the discussions on fundamentals of parallel computing and OpenMP was over, and the main discussion on that live session was based on the concepts we have covered in the first two modules. But right now MPI has been covered, and MPI, you can understand, altogether works on a different paradigm of parallel programming, which is uh, distributed computing, distributed memory parallel programming. We have also looked into MPI programming, and one practical example using MPI-based parallelization for scientific computing problems has been discussed in detail in between, which is domain decomposition method. And I've shown how to parallelize a matrix solver using domain decomposition method, and how you actually can solve Laplace equation for a for a practical problem using domain decomposition method in multiple CPUs in a distributed memory system. Those parts have been already discussed. Now, today's discussion can cover part of MPI parallelization ideas, and we'll also, I think 7 weeks lectures are uploaded, so you probably have also looked into GPU programming, CUDA programming for GPU parallelization. And this is also a new paradigm, because GPUs do not work as CPUs, though threaded parallelism works in GPUs, but GPUs has certain differences in CPU with CPUs in terms of memory management, in terms of thread launching, in terms of control, in terms of latency hiding, etc. And they are massively parallel infrastructure, in that sense that you can have a number of processors available for GPU computing, which are thousands, few thousands cores are available in GPU computing. So GPU is altogether different from CPU computing, and we'll also discuss on GPU computing in today's live session. I cannot see any question posted in the forum, but in case, just look back into it. In case you have some questions, you can type in the chat window. This, I told you, an important purpose of this discussion is that at this stage, because we are discussing number of different parallel programming algorithms and and which are quite different from general CPU computing ideas. So therefore, it is important that we spend some time on these discussions. I'll try to give you some revision of which we have discussed in the video lectures, but in again, in case you have questions, you are welcome to ask those. Okay, so I think we had enough discussion earlier on OpenMP based parallelization. Uh, we had sufficient discussion on fundamentals of parallel computing, but some of the concepts are still important, both from fundamentals of computing, where we have discussed about distributed memory and shared memory systems and their comparisons, and also with OpenMP, because in OpenMP we have introduced threaded parallelism, and if you look into GPU-based systems, threaded parallelisms are important here. So let me quickly revise through the topics that we have discussed earlier on MPI programming. So first thing is that MPI works in a distributed memory system. A distributed memory system essentially means that there is no global memory. Each processor reads on its own local separate memory space. Having said so, we can still have a distributed memory programming running in a SMP or symmetric multiplexer type of environment. Like if I consider my own desktop or laptop, it is a single motherboard computer where multiple processors or multiple computing cores are there, and all of them are connected with a single memory space. However, so if I define any file, that should be visible to all processors. However, when we run an MPI program, each processor or each core or each virtual processor gets a separate memory space and works on that memory space only. If processor A identifies an array, if processor 1 identifies an array A, processor 2 will also identify an array, but these two arrays are never same in a distributed memory system. These two arrays are physically different address spaces. So if I do some changes in the array A, which belongs to processor, which was done by processor 1, it is not readily visible to other processors. That is the main issue of MPI programming, that the entire uh, program is run in multiple processors, and each processor it looks into its own separate distinct memory space. In case of large computing platforms where many computers are connected through a switch, each processor is looking into the physically different memory spaces. In case of a single motherboard system, or say an SMP or a hybrid system where many multi-core computers are connected through some interconnect switch, even then each processor is looking into its same separate address space, though these address spaces may locate in the same physical memory unit, but these are different address spaces. But each processor, if I say again an array A, each processor is looking into an array in the array A, in the name of that address space is same, and the way each processor is accessing that will also be same, unless you do something else. Now, when you run an MPI program, first thing is that MPI environment has to be initialized. MPI init is there. Then you define the communicator, MPI com word. So all the processors which are inside that program are part of that communicator. Now, when you launch the MPI program, each line of the program will be executed by all the processors independently, unless otherwise you use some if-else condition and ask some of the processor to not do that. How to use this if-else condition? For that, each processor should know what is its unique ID or rank. So MPI rank is an MPI, again an MPI function which let every processor know its own unique rank. And if you have to use say that some of the processors will do some job, some of the processors will not do that job, then you have to specify that the processors with some specific IDs will be doing that job, the other processors will not be doing that job. So that specifications has to come there. So these two are kind of very important part here. That first is that if nothing is specified, each processor will execute its um, own task. And each processor will execute the same task which is specified by the MPI program. So any line in the MPI program will come to each processor. If some processor is not supposed to work on that part, it is programmer's responsibility that he will specify that the processor should not work on that part through certain if-else type of command. So these are two important aspects here. Now, if we further look into the fact that once the MPI program runs, what happens? So each processor is asked to work on work on the lines, execute the lines which is inside the program, and whatever changes it is making, that change is specific to its own memory. It is a distributed memory program. By the way, MPI-3 has shared memory feature also, but we are not going into that advanced stage. We are discussing basic distributed MPI programming. So in that case, if shared memory feature is not enabled, by default setup, each processor is working on a distributed memory system. So each one, whatever it is doing only in its local address space. Processor A is doing it, processor 1 is doing its own local address space, processor 2 is doing its in local address space, processor 3 is doing the same thing in its local address space. They are not writing to any common global address space. There is no global address space in MPI program. If the programmer needs to think in terms of global address space, he has to make some virtual, he has to make it inside his mind or inside the algorithm, that what even virtually the software wise there is no global address space, but he can think that this can be thought a part of the global address space, this can be thought a part of the global address space, and use right mapping. However, all the processors can write to files to the same disk space. So where the files are being written, the I/O that can be done, that is done to a common file system. A common file system can be used. But the program memory, what is in the RAM, that is different for different processors. But now, for continuity of the data, for smoothness of the solution, and for many factors, we need to update other processors about what is done by one particular processor. And how is it done? So first, another important issue comes that each processor knows about its own rank, but it should also know about the rank of the other processors. It cannot let the rank of other processors independently known to each processor, but what it can know about, that what are the processors available, what is the total number of processors available there, and that is obtained by MPI com size. So when MPI com size is executed, the size of the communicator or the total number of processors inside the communicator is found out. And if the total number of processors coming through MPI com size is 10, that means there are 10 processors who are executing this program, and their rank should start from 0 to 9. My com size -1 is the maximum rank, and it will start from 0. Having said so, how this number is specified? In OpenMP, we have seen that the maximum number of threads, or let us say the number of threads is specified through environmental variable set env, or while executing a parallel regime, we can specify the number of threads. In MPI, there is no environmental variable to specify the number of threads. It is specified by the execution command. In the execution command itself, one is to specify what should be the total number of threads. So that is how an MPI program should work. That when MPI command is given, not total number of threads, total number of processors are specified. Now, what I was discussing is that some of the processors have updated some data which other processors need to know. So what can be done then? So if data has to travel across processors, what should be the modality? And for this, it is important that there should be some communication across the processors. For example, there are 3 people and someone got some money, others need to get some other needs to borrow from him. How is it possible? You need to communicate. You need communication among themselves. And so precisely that is why communication is extremely vital in data transfer, in MPI data transfer, or data transfer or communication. They are synonymous in an MPI program. So one processor, memories are different. Each processor has different memory. one processor needs to inform another processor about some changes it has made in the memory. And that will be done by transfer of data across the processors. There is no common memory mapping. So whatever is happening, it is processor to processor, peer-to-peer communication. And this communication is in terms of transfer of some data. Some processor is sending data, the other processor is receiving it. And this data transfer can be done in a couple of ways. One is a collective communication, another is called point-to-point communication. As the name suggests, collective communication means I have a mic and I'm announcing it in to everybody. Like what I'm doing right now is a collective communication. I'm making a live and announcing it to everybody. Instead doing that, if I had phone call with one of you, that would have been a point-to-point communication. So if one processor needs to inform other processors about some changes in the data, it will be a collective communication. As a whole, it is communicating it. If one processor needs to get information from all other processors, that is also collective communication. But if one processor needs to inform or give some data or take some data specifically from one particular processor, then it would have been a point-to-point communication. I got a question from Vishya Jairam on how can I create a artificial intelligence. I'll come back to the discussion, but let me look into the question. Unfortunately, this is not a course of artificial intelligence. Artificial intelligence is altogether a different subject, though high performance computing techniques are being used in artificial intelligence these days. In general, what is artificial intelligence? That uh, how one becomes intelligent. One becomes intelligent by ability of processing information. So artificial intelligence means you have to provide certain information to the system and then give program the mathematical tools which will give it the ability to optimize some data to extract information out of it. And now with the pattern of the information from the data, how from the set of data, how we extract the information with that pattern, if you get a new data set, you have to predict what is going to happen there. So this is intelligence means so that you are able to predict what is happening to a new set. So you have to train the programming model with available data and the results, available input and output, and then give a new and then find out a relation between them, and then ask uh, the program to take uh, take a new input and predict the output and see if the output is right with the actual value. So this is a different altogether a different set. However, training the model and writing the right optimization algorithm is the same thing. So training the model and writing the right optimization, these are some of the important parts here. Okay. Uh, Sanjuda, Okay, we had some technical problems, so I'm restarting this session. So we're discussing about artificial intelligence in response to Vishwa Jayaraman's question. So it can be seen that this is artificial intelligence, as I said, is a different field of study. However, in order to process the information, in order to collect the data, and sorry, in order to get an optimized solution from the data and find out the optimization functions, find out right parameters, and then uh, extract it from a large data set and then applying it to a new data, these things are computation intensive, and therefore we many times use some efficient matrix solvers while working on artificial intelligence problems. And these solvers can be parallelized using some of the HPC techniques. And especially when we talk about GPUs, it is seen that GPU cores can be very efficiently utilized for artificial intelligence problems. And this is another field of HPC, using HPC in artificial intelligence. So that is for giving you faster result in artificial intelligence problems. However, artificial intelligence is not same as HPC, is not in general a part of HPC, but HPC can be utilized to get faster solution in artificial intelligence. Well, if you are interested in AI, you should take a you should study it thoroughly. And HPC can be a good example. AI can be a good example in showing how HPC tools can be used efficiently for getting faster solution. But in general, it's a different field. Well, so we are discussing about MPI based programs. And as I said, that the communication is important in MPI in order to transfer data across multiple processors, because each processor has its own separate memory space. Now, how that can be done? What are the techniques for doing that? And that is another very important question here. To appreciate that question, we again have to think that the processors are working on their separate memory space. Now, only the programmer knows when data extracted or data modified by one processor will be required by another processor. This information is not with any generic program or with the software or with compiler. Programmer knows the algorithm, and then only he can tell that, say I'm summing up 100 numbers in 100 processors. Total is 10 to the power 4 numbers which is to be summed up. Each processor is coming with its sum. Once this sum of 100 numbers will be done, then it has to be communicated to another processor, which will take all the 100 sums from all other processors and sum it up and give you the final solution. So for this particular problem, only the programmer knows that once 100 number sum is done in one particular processor, it will communicate the data. So it will send the data to another processor. So data transfer, data communication is the responsibility of the programmer, that he has to specify it within the program. At this stage, processors have to communicate data. To which processor it will communicate, that is also programmer's responsibility. If you look into OpenMP, it is kind of automatic. You know that the threads have calculated these numbers and write just a reductional pragma, or sum it up from the private variables, put it into shared variable, etc. And this is automatic, how the data is coming from different private variables and being summed up into a shared variable. But if you go into OpenMPI, it's not automatic. It's not compiler driven. Automatic means in OpenMP, this was being driven by compiler. In MPI, this is not compiler driven. One serious issue we looked into OpenMP is race condition and false sharing, because everything is written to a same data location. But in MPI, they are writing into different data locations. So false sharing, different address spaces, false sharing, as well as the shared memory issues like contention, race condition doesn't appear here. A programmer has to specify that data has to go from one processor to another processor. And this transfer is in two ways. One is collective, when programmer knows that this data has to be broadcasted to all the processor, it's collective. When something like reduction is happening from all processors, data will be taken and reduced to one particular value. It's again a collective operation. When one particular processor needs to give information to another particular processor, it is point-to-point communication. Collective communications are usually broadcast, which is bcast, scatter, take a data, scatter to all different processors, get data from all processors and collect it in one particular processor. Any collective communication with all gather means all processors will do the gather. Is uh, is a collective communication, which is the same communication happens in all the processors. Reduction, you have to find out summation of different numbers, like the example I was giving for 100 numbers, 100 processor, it's summing of 100 numbers. If you do simple reduce, the particular processor which has asked to do the reduction will reduce the value. If you do all reduce, all the processors will reduce the value. Now, this communication calls are processor specific. Each MPI line will be executed by all the processors separately. But communication is processor specific, so programmer has to identify the processor which is communicating and the other processors with which it is communicating through the communication directive. In case of directive, it's a function call. In case of directive in MPI, through the function, in the function call itself, the processor who is sending data or receiving data, and from the other processor where it is sending or receiving data, has to be specified. In send receive type of operations, as it is the processor in which is executing the send command is sending data from which it is specified. Now send receive like bcast, scatter, gather, reduce, these are collective calls. Send receive and its different variation are point-to-point communication call. If we write simple send and receive, they are blocking calls, that one processor will send data to another processor. There should be another processor whose name is written in the send command executed, send call executed by the particular processor. The other processor will also have a receive call, and the ID of the sending processor must be present there, and they should match, tag should match, etc. Then send receive will happen. This is a blocking operation. That means when one is sending data, unless this data is received by the right processor, this processor cannot do anything. So I'm giving somebody something, unless he receives it, I cannot do anything else. So this is called a blocking communication. And receive is also send has to be matched by a receive has to be matched by a send, etc. But so in some point of time, this blocking can add up to latency in the overall processor. So this may not be advised in those particular cases, and therefore instead of simple send receive, we use something like bsend or isend, which are non-blocking commands. So even if the data has been sent, till it is received, till the receiving has been done successfully, the processor should not be on wait, it can do something else. Then this is called communication computation overlap as the time, because communication and computation are two different execution, to different processes executed by the processors at one time. When it is communicating, at the same time communication is done through network channels. When the data is passing through the network channel, at the same time processor can crunch numbers and carry on computation. Now so one of the important aspect is that the programmer has to specify the communication instances, and programmer has to specify the pathway of communication. Programmer has to specify where it will be blocking communication or unblocking communication, etc. Compiler cannot do automatically all these things. In OpenMP, compiler was responsible for many more things. In MPI, compiler is not responsible for these things. But also an advantage is that the issues like false sharing, etc. are not present. There can be an important question that any collective operation, that means one processor is sending data to many processors, can also be replaced by multiple send receive operation. However, collective operations are more optimized because the processors are connected to some network topology. It uses the information of network topology and does the communication very much more efficiently compared to individual send receive. And send receives by each processor are executed in serial. If one processor has to send data to 3 different processors, it will do it sequentially. So there is also a sequentiality overhead in multiple send receive operation. Any sequentiality will give overhead. If a large amount of data has to be sent from one processor to another processor, one important question is that can it be done in multiple passes, or it should be done in a single pass? Each send receive operation has its own startup time. The processor has to find out the receiving processor and then see whether it is okay for data transfer. So if we take a large message and break up into small messages and do send receive operation, each operation will require a startup time, therefore total communication time will increase. So these are few important questions that if there are few processors, one processor has to give data to some of the processors, some other processors, distribute data. Will it be good if it distributes to many processors in terms of communication, or it will be good if it sends the data only to one processor? Again, if it is sending to many processors, it will not happen parallelly. It will happen sequentially. And each time there will be, it's like sending executing many send receive operation. Each time there will be some startup time. There will be more communication. So based on that, we have to be very judicious in communication. And communication typically has much more communication typically requires much more time than computation. So it is also important that we see communication by communication requirement in the program, and the total amount of communication for each unit of computation should be brought down. An efficient MPI program should have less communication and more computation. But communication is inevitable. You cannot avoid communication because there will be requirement for continuity of data, etc. That that one person knows about what is happening in another person. Now, one of the example we have seen is domain decomposition, where we took a Laplace equation. We looked into how to parallelize Laplace equation also. We took a Laplace equation and parallelize this Laplace equation for parallelize this Laplace equation. Sorry, we took a Laplace equation, use a numerical method to write down the differential equation to difference equation, and then parallelize this equation. So this communication to computation issues are more serious here, because how many processors you'll use for that? When you parallelized it using domain decomposition method, each processor gets small amount of data and works on that. And now for continuity of data, each processor has to exchange data with the neighboring processor so that the entire domain is gives a continuous solution and you get the right solution. So what should be the number of domains so that you do less computation, still do good, you do good amount of computation compared to communication? These are important questions. If you are having a large problem, you can use large number of processors. Computation is only done for the internal points, while communication is done for the internal point. Communication is done only for the boundary points. So one idea should be the number of boundary points. The boundary should be drawn in a way in between domains so that number of boundaries points can be less, kept less. Now, when computation and communication both is happening, the speed will increase if computation is more and communication is less. However, if computation in a particular process, even if you run a single processor job, then everything is computation, no communication is there, but it is not advisable. It will take more time. So you have to look into the problem size. If problem size is large, you can use, and this goes to the classical theory, if problem size is large, you can use more number of processors, and therefore computation is internal points, which is large also, but it is reduced compared to the large whole problem, a single domain approach. Also, communication is there, but if the problem size is large, communication by computation ratio is right, and your efficiency is good for large number of processors. If problem size reduces, then you have to use less number of processors, else you will end up in doing many communication compared to the computation. So it will be a slower progress. The domain decomposition is a very important example where we take a large problem, we break it down into multiple small problems and try to solve them independently in different processors parallelly while exchanging data across the across the boundaries to get a converse solution. Domain decomposition is extremely important from that perspective. Now, another important application, domain decomposition is used for matrix solvers, for solving a Laplace equation, which basically requires matrix solver. It's an iterative method in which you get a globally converse solution. Another way of parallelizing matrix solver is data decomposition, which is more like shared memory parallelization, but here we are utilizing it in in distributed memory environment. That some of the rows of the matrix is given to some of the processors, and the matrix vector product, which is stem of any matrix solution solver algorithm, is carried away to the smaller submatrix given to each of the processors. And the communication needed is to find out the matrix vector product and assemble them as a single vector. So some of the vectors have to be exchanged using a collective call, or mostly using a collective call. Point-to-point communication is also possible, but mostly using something like gather vector communication. Data parallelization is also an very important part in MPI based matrix parallelization, and sometimes because your computation is actually less in data parallel environment, sometimes you can handle much efficiently, you can handle the problem. But domain decomposition has its own advantage because you are working on a small submatrix, you're reducing the memory requirement in domain decomposition. There are some specific advanced MPI command, like MPI card create, etc., which are focused towards a Cartesian matrix parallelization using MPI calls. We have discussed those calls also. They are features of advanced MPI, but if you are trying to write an efficient program, instead of in the first few lectures on domain decomposition, I have shown you that without knowing any features of advanced MPI, just by knowing basic MPI, 6 basic MPI calls and one all reduce call, you can parallelize any matrix solver. But if you use the advanced MPI functions, you will get faster. You can get faster result because they have much more optimized features. Well, so after MPI, another important topic which we have read is CUDA parallelization, GPU-based parallelization. I hope that we'll have another session on GPU parallelization, and we'll spend, if possible, we'll spend another session on GPU parallelization also. But if we quickly revise or discuss what I've shown you in GPU parallelization, one aspect is GPU hardware, which is very different from CPU hardware. If we think of a CPU, we think of few processors, 2 processors, 4 processors, etc., and which is attached to a large memory. If we think of GPU, we think of some memory, but a large number of processors attached to that memory. So GPU usually comes with thousands of processors, 2000 processors, 3000 processors. And these processors are called GPU cores because they are not similar as CPU processors. They are very simple rudimentary units of number crunching, of doing arithmetic and logical operations with small control but large number of registers. They cannot execute a complex control if-else statement type of algorithm. They have a different scheduling than CPUs, etc. They are, in some sense, they are very different from CPUs. However, we can utilize them for getting faster solution. GPUs are initially developed for gaming purpose, so they are not primarily designed for high performance computing. However, as it is observed that matrix computing can be done efficiently using GPUs, nowadays GPUs are being heavily used in high performance computing, especially in science domain, in science engineering domain. One point is that GPU is an accessory. You cannot directly write a program to run on a GPU. You have to write a program which will run on CPU, and you have to mention some part of that program that will be offloaded to GPU. And this is done, one of the largest GPU vendor is NVIDIA. And this is primarily done by NVIDIA through a programming paradigm called CUDA. It was initially named as Compute Unified Device Architecture, but now they name it as CUDA. CUDA is like an API which has all semantic syntaxes required for, you have to include CUDA in your C program, and this will be a .cu program then instead of .c. If it's Fortran, it will be .cu program, .CUDA Fortran extension program, and it will primarily run on CPU. And when something called a kernel function is launched, that part of the job, kernel function, will be launched in the GPU, and it will be launched in many GPUs altogether. The total number of kernels will be specified by specifying the block and thread block size and grid size, and that many threads will be launched to run over large number of GPU cores. The GPUs have thousands of cores. If many cores are there, there will be very heavy high latency. However, GPU has a technology that they hide latency through scheduling of cores, that how jobs will go to each course, and that for that looking into GPU architecture is important. That what are SMs, streaming multiprocessors in GPU, what is an warp size, how jobs are mapped into a streaming a block, how blocks are mapped into streaming multiprocessors, and how warps of blocks are activated. And essentially, when a GPU program kernel runs, some of the, not all the GPU cores are populated, but some of the GPU cores are populated. Even that is a huge number. And threads and different threads run on these nodes independently. So it's a threaded program using single instruction, multiple data parallelization algorithm, very similar to OpenMP in the structure, but it has certain differences, like instead of running in CPU or running in GPU. And also, though we have unified memory now, but the conventional practice is that GPU memory is separate from CPU memory. So if something has to be executed by GPU cores, the memory has to be copied from CPU to GPU by CUDA mem copy. And then once GPU cores are active and writes on that same memory space, it is copied back to the CPU, again using CUDA mem copy, and we have to write what is the direction of copy. CPU, which hosts the GPU card, is called the host, and the GPU is called device. So whether host to device or device to host copy will be done, that has to be specified. It is important to understand GPU architecture. It is not that important to understand symmetric multiprocessor architecture before you go to OpenMP programming. You have some basic idea, you can do OpenMP programming. It is somewhat important to understand distributed memory architecture, hardware architecture, but not in much detail before you do MPI programming. If you only know that each processor writes to its own memory and then communication happens across processors through the network cable, it is fine. But if you try to write a GPU program, it is important that you understand GPU hardware. And we have discussed GPU hardware is also evolving with time. Every time NVIDIA or AMD, the GPU OEMs coming up with certain changes in hardware, certain changes in the compute capability also, which are some way hardware, some way software dependent. So, however, with the latest version of GPU available, because GPU is not a very old technology, it's a very new technology. So it is not that over 60 years GPUs have been developed. So with the latest version of GPU available, we should be some way conversant with the hardware and architecture of the GPU, and also the programming paradigm there. If we do not understand the hardware to certain extent, it will be difficult for us to program GPU. But again, for science and engineering purpose, why should we need to understand computer hardware? We need to understand it to get efficient program, which is going to help us in our costly, large scientific engineering problem solutions. Uh, Two important thing is that GPU memory, GPU programs do not directly run on GPU. So a program which has a GPU component has to be called from, should be a part of a CPU program, and CPU should launch certain function to run on GPU. That those are called kernel functions. And kernels will be launched as threads, which will be active over different GPU cores. How these threads are scheduled, how these threads will run, that require understanding of hardware as well as CUDA, how CUDA functions. Also, GPU memory is usually different from CPU memory, except unified memory. We will discuss unified memory at the end, but at 8th week. But let's go to more conventional way, non-unified memory, where CPU memory is separate, GPU memory is separate, and when data is copied from CPU to GPU, then only GPU threads can work on that. Even within the GPU memory, there are multiple layers. There is certain hierarchy of GPU memory. Some memory resides in the GPU RAM, device RAM, which is read by the GPU cores through a slightly more latent interconnected. And some of the memory can be copied on the symmetric multiprocessors itself, which are much faster read, can be much faster read by GPUs, but the size of that memory is small. So you have to be smart enough to consider which memory will be taken and how will it be copied to the GPU chips, which can be which will have less latency. And GPUs have many registers, and these registers are used for latency hiding. So these concepts are important. I think as you go through the slides and the lectures, you will get some of these components, and it is of great use that NVIDIA has who is one of the leading GPU manufacturers. They have very good uh, documents on GPU programming, CUDA guide to CUDA program, both in C and Fortran. Also best practices for GPU programming and white papers on GPU hardware architecture. I have given references with the slides, and these are free documents. If you download it, read through it, you will understand a lot about. And this is the only available main source of material to outsiders, to users for writing GPU program and utilizing GPU. So these are important things to read. I think if you're interested in GPU programming, you must read through NVIDIA's own documents. And GPU programming it's very important to understand about GPU programming, learn GPU programming, because GPU is showing huge capacity in giving you faster solution, huge potential of good high performance computing programs can be developing good high performance computing programs for large scientific problems are with GPUs. And it is much easier to maintain a GPU. If you think of a system which will give 100 times speed up compared to a single processor machine, if you think in terms of a distributed memory system, you will need a large rack which has to be maintained with right air conditioning, etc. And many blades will be there with different processors, and that can be used for MPI programming. But if you try to do the same thing using GPU, you need only a single computer box and only a GPU card. Though cost is not probably comparable, but energy and maintenance are much simple in GPU compared to a large distributed computing system. However, GPU programming is complex. GPUs have uh, I'll come to Pushkar Pandit's question in a while. GPU programming is complex. GPU has its own memory issue. GPU programmers need to understand certain things about hardware and CUDA and types of drivers, etc. And that makes GPU programming a little difficult. However, GPUs have much higher potential. So Pushkar Pandit's question is CUDA a standalone platform or can we merge CUDA and MPI? This is precisely discussed in last lecture where we'll discuss about in 40th lecture, I think, where we'll discuss about hybrid programming using multiple GPUs. CUDA is usually standalone. So when you write a CUDA program, it is supposed to run on a single GPU card. But if you have multiple GPUs, in order to communicate among these GPUs, there are some technology called NVIDIA Direct from NVIDIA. But usual way is that you distribute the job through domain decomposition into multiple CPUs and put GPUs on those CPUs. So communication across the CPUs will be done through MPI. So MPI and CUDA can be coupled in a single program, but they are essentially standalone APIs. They're standalone APIs, but they can be compiled to get a hybrid program, hybrid CPU GPU program, and this is discussed in 40th lecture. Okay, if no other question is there, Pushkar, you will probably have one more session after 40th lecture. I'll see how it can be arranged because two live sessions were promised through the NPTEL course, but we'll try to have one more session. And I request you go through the hybrid computing discussion, multi-GPU programming slide, and then we can discuss it in much detail. And any very large computing effort, today we are talking about exascale computing, petascale, exascale computing. All these large computing efforts are essentially hybrid computing where multiple GPUs are used and they are connected to different CPUs which are communicating via MPI. Okay, we'll learn through it once you cover this. So we are at the end of today's session. If you have doubt, you keep on posting on the forum. I have given you some example codes on MPI and OpenMP. Hope you can try those things. I'll give you some example next week. I'll give you some example codes on CUDA. You can look into CUDA programs from there. But somebody asked for CUDA programs also. But again, I'm telling you, NVIDIA's CUDA C programming guide or CUDA Fortran programming guide is the best resource for learning CUDA. There are many programs available there, parts, program snippets also available there. Even if I show you any program for this class, it will be developed based on those programs only. So it is important that if you want to learn CUDA, you download those documents and look into the programs there. You can start executing those programs if you have a GPU card in your computer. If you do not have a GPU card, then it is difficult. But I told you that National Supercomputing Mission is establishing many parallel computers across the country. So if today a GPU card is not available, some GPU cards are not that expensive, you can afford it yourself also. But in case it's not there, in a year or so, you might find it easy to access GPU platforms and practice that. GPUs have great potential in high performance computing. If only stopping factor is that resource not available to you, do not leave the GPU part. Read through the GPU part, try to understand it. It is not always necessary that you do hands-on session to understand some basic nuances of GPU hardware and programming, and that is going to help you later. Well, so we are continuing with GPU in our regular in this course, in the classes, in the video lectures, and after this we might have another session where we also can discuss a little bit about the exam pattern. It is also another request that everybody take the exam seriously and try to write the exam, because this is kind of a programming course. Though we are not giving any programming assignment here, this understanding high performance computing requires understanding on parallel programming. If you prepare well for the exam just by looking into the assignments and slides, you will develop some ideas which is going to help you for the programming. When you will get the practical programming assignments, it will help you. So it is important that you prepare for the exam and take the exam seriously. Okay. Is there any commercial CFD software? Yes, ANSYS Fluent uses GPUs. ANSYS Fluent now, ANSYS Fluent has GPU programming. There are other also, I think, um, Star CCM also have GPU. There are commercial software with GPU, but ANSYS Fluent definitely has GPU in CFD. In mechanics, Abacus has GPU version. So many open from also has a GPU, which is a open source software, also has GPU components, but which is not that popular right now. But all these software, both commercial and open source, are coming up with GPU versions. So those will be, if not available today, those will be available in couple of months. But ANSYS Fluent has GPU component. Okay. If no other question, I can end today's session. Just wait for a couple of minutes if I see any other question. Else I'll end today's session. Other question, I can end today's session. Okay, thank you all for your attention, and attend the video lectures and try to solve for the assignments. I hope I'll meet you at least once more before your exams, and prepare well. All the best for the exam will be also not very far away. And any doubts, anything else, you can write to the forum. I keep on checking the forum, and I'll answer. Okay, thank you.
Thank you, sir.
Thank you. So, Bivangshu,
Yes, sir.
is it over?
Yeah, yes, sir.
I'm quitting. Thanks.
Okay. Sir, you can close now.
Yeah. Thank you, Bivangshu.